When we talk about artificial intelligence agents, most people imagine a conversation. You ask a question, the system answers. It feels like it remembers things. We usually explain this with a simple model. Short-term memory for the current conversation. Long-term memory for everything learned over time. This is the standard three-level framework. It sounds logical. It mirrors how humans remember things. But when we push these systems into high-scale, multi-agent environments, this model breaks. It fails in ways that are not always obvious until the system starts drifting. Here is the thing. The standard model treats memory like a hard drive. It assumes that if you store something, it is there when you need it. But in complex systems, agents do not just store data. They negotiate, they conflict, and they evolve. When multiple agents work together, a simple retrieval system becomes a liability. If Agent A tells Agent B something, and Agent B updates its internal state, that information needs to be consistent across the network. The standard framework does not account for the friction of that consistency. Let us look at the first level, short-term memory. This is usually tied to the context window of a large language model. It is the immediate conversation history. The problem here is not capacity, it is decay. As the conversation grows, the signal gets lost in the noise. This is known as context drift. An agent might forget the original instruction because it is buried under thousands of tokens of intermediate data. In a single agent task, you might get away with this. In a multi-agent system where one agent is waiting for another to finish a task, that drift causes cascading failures. The agent acts on outdated context. Now consider the second level, long-term memory. This is where systems store facts and experiences in vector databases. It is meant to be permanent. But permanence without management is dangerous. If an agent learns a fact that turns out to be wrong, that wrong fact stays there forever unless explicitly removed. This leads to hallucinations and contradictions. The agent will confidently state two things that cannot both be true. The standard framework assumes retrieval will find the right information. It does not account for the quality of that information over time. It treats memory as a passive archive rather than an active resource. This brings us to the third level, which is often missing from the standard discussion. We need a memory operating system. This concept proposes a layered approach that separates transient working memory from persistent long-term storage. It introduces mid-term memory for active projects. It handles the dynamic updates required for stability. Without this layer, agents suffer from error accumulation. Every interaction adds a small error. Over time, these errors compound. The agent becomes less reliable the longer it operates. To solve this, we need a mechanism called adaptive crystallization. Think of it like sedimentation in geology. Raw data is like loose sand. Over time, it settles into rock. The system must automatically filter, summarize, and consolidate experiences into durable knowledge structures. It should not retain all raw interaction history. That is inefficient and noisy. Instead, it should extract tacit knowledge. This reduces the cognitive load on the agent and prevents the accumulation of contradictory data points. Implementation requires moving beyond generic vector databases. You need explicit memory control mechanisms. One crucial feature is automated contradiction detection. The system must know when new information clashes with old information. It needs recency-scored retrieval to maintain coherence. If you ask an agent about a project it worked on 6 months ago, it should prioritize the most recent state of that project, not the initial setup. This ensures the agent remains coherent over time. There is a divergence in implementation philosophy. Some propose operating system-inspired architectures with first-in, first-out and page-based organization. Others favor bio-inspired controllers that separate artifact recall from state commitment. The goal is stability. You want the agent to recall an event without committing to a change in its core state unless necessary. This ensures robustness. The research on memory in the age of artificial intelligence agents suggests that we must categorize memory by forms and functions. We are talking about token memory, parametric memory, and latent memory. These serve different functions like factual recall, experiential recall, and working recall. The community consensus is that current memory solutions are insufficient for complex autonomous tasks. We are driving a shift towards specialized, universal memory layers. These layers function as a distinct operating system component for agents. This allows for trustworthiness and multimodal capabilities. We are moving toward formalizing memory as a first-class primitive. This enables robust, personalized agentic intelligence. However, there is a significant knowledge gap. There is a lack of a unified benchmark for evaluating memory quality across different architectural styles. This hinders comparative analysis. We do not yet have a standard way to measure if one memory system is better than another. Future directions must address this trustworthiness issue. We need to know that the memory is reliable before we trust the agent with critical tasks. In the future, the question will not be how much memory an agent has. The question will be how well it manages that memory. The standard three-level framework is a starting point, but it is not the destination. We need to move from passive storage to active management. We need systems that can detect when they are forgetting or when they are lying to themselves. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.